Chemistry is the study of the composition, structure, and properties of matter and the changes it undergoes. Composition means what something is made up of. Structure is how those things are put together. And then the properties of that matter, what it exhibits, and we'll talk about physical properties versus chemical properties here in a second, and the changes it undergoes. We're really interested in energy, and that is whether energy is released or absorbed. It's a big focus in chemistry and in this class. A chemical is any substance that has a definite composition. That means it's made up of the same thing every single time. Now, normally we think of chemicals as maybe stuff that I have in my chemical supply room, or maybe the cleaners that you store underneath the kitchen sink. But with this definition, you can see it's much broader than that. Water, oxygen, and salt are all chemicals under this definition, even though we don't necessarily associate them as chemicals in our everyday life. They do have that definite composition. Now, there are several branches of chemistry. In this class, we're going to focus on inorganic chemistry, and that's the study of matter that does not contain carbon. Organic chemistry is the study of matter that contains carbon, and is useful in pharmaceuticals, polymers, and making of new fabrics. Biochemistry is the study of the chemistry in living things. Pharmaceuticals and genetics, this is a very emerging, fast-growing field. So if you liked biology and you find that you like chemistry, this is a great subject to pursue in higher education. Physical chemistry talks about the physics of chemistry, and those are the forces of matter, the forces between molecules. Much of it is computational, and they develop theoretical ideas for new compounds. Analytical chemistry is the study of high precision measurement. Forensics, quality control, and medical tests are all part of analytical chemistry. Now, the language of chemistry. We'll start with a few basic words. Matter. Matter is anything that has mass and takes up space. The air in the room is matter. It has mass. It's a tiny little bit of mass, but it does have mass, and it takes up space. Mass is to measure the amount of matter. Now, it's different from weight. Mass is the amount of matter that is there. Weight is the effect of gravity on that matter. So mass just doesn't have gravity taken into account. Volume is the amount of three-dimensional space an object occupies. You've dealt with volume in your math classes a lot. Length times width times height if we're trying to find the volume of a rectangle. We can also measure volume in liters or milliliters or gallons. It's usually associated with a liquid, but we can find the volume of solids just as well. Describing matter. Matter has intensive properties, and these do not depend on the quantity of matter. It doesn't matter how much you have. It's the same every single time. Temperature. It doesn't matter on how much of a substance you have. If that's its temperature, that's its temperature. Extensive properties depend on the quantity of matter. It matters how much stuff you have if you're going to get the mass of something. It matters how much volume you have, or it matters how much stuff you have when you're trying to measure volume. So those are extensive properties where it depends on how much of the substance you have. States of matter. Solid. Your middle school definition, definite shape and volume. It's not going to change. In this class, we are going to talk about those states of matter, but we're going to go a little bit deeper and talk about the particles that make up that matter and why it has definite shape and volume. We would visualize the particles of a solid being very close together, maybe something like this. Not a lot of space between those particles. So they're not easily compressed. If you tried to squish a solid, it's not going to squish very much because there's no space in between these particles. A liquid, for our middle school definition, is definite volume and no definite shape. If you have 50 milliliters in one container and you transfer it to a different container, you're still going to have 50 milliliters, but the shape would be different. Liquids flow. Their particles can move over and around one another, and that's why when you turn a cup on its side, the liquid inside flows out. We would visualize the particles as still being pretty close together, but they have enough energy and are able to move over and around one another. So here you can see that these particles are taking the shape of their container, but they're still pretty close together. So again, we're not going to be able to compress liquids that much because there's no space to get rid of. Gases, on the other hand, have no definite shape or volume. They also flow. We visualize them as particles being very far apart in constant random motion. So that means they're going to go until they hit a wall, and then they're going to bounce off and continue moving. So particles, we can visualize them like this. Now, gases are compressible because there's lots of space in between these particles that we can get rid of. Because they're in constant random motion, they can expand to fill any container. So they will just continue moving, and that's why you can smell things like fingernail polish remover as soon as you walk into a room, because those particles are moving. Physical properties. Physical properties, or a physical property, is a characteristic that can be observed or measured without changing the identity of the substance. And that's a pretty important part of the distinction between physical and chemical properties. Physical properties, it can be measured without destroying that substance. So some things that are physical properties: color, state, what physical state is it in, solid, liquid, or gas. Those are things you can observe without destroying the substance. Boiling and melting points. When you boil water, you don't destroy water. You separate the water molecules. And so this is a physical property, but often students get that very confused. Melting point's the same thing. When you freeze water, you don't destroy water. You just make those particles stop moving around. So it's still water, and that is a physical property. And it can be very useful in identifying substances. Oftentimes we will do melting point determination to identify what a substance is. Physical changes is a change that does not involve a change in the identity of the substance. If I have a piece of paper and I tear it in half, I have not destroyed paper. I still have paper, but it's in smaller pieces. So grinding, cutting, breaking are all going to be physical changes. When I dissolve sugar in water, I don't make a new compound. I haven't destroyed sugar. I haven't destroyed water. I just have sugar floating around in water. So again, that is a physical change, and often something that students will be confused on. So dissolving is a physical change, and so is a change in state. We talked about this: melting, freezing, vaporizing. When water changes from liquid to steam, water has not been destroyed. The molecules have just been separated and are now able to move around more. So they don't just change the identity of the substance. The fundamental building blocks of matter are atoms and molecules. Atom is the smallest unit of an element that maintains the properties of that element. Now, an atom can be broken down further into protons, neutrons, and electrons, and neutrons and protons can be broken down even further into quarks, but an atom is the smallest unit that still maintains the properties of that element. So you wouldn't be able to tell a proton of carbon from a proton of oxygen, but you can tell the difference between a carbon atom and an oxygen atom. An element is a pure substance made out of only one kind of atom. So copper, iron, those are all elements, and we have the periodic table of elements, and we'll get to know all of those elements as we're going through, or at least most of them. Now, a compound is a substance that is made from the atoms of two or more elements that are chemically bonded. So my example here is water. It's two hydrogens and one oxygen. This is a subscript, this 2 right here, and it tells me how many of the preceding element I have. So it's 2 hydrogens and 1 oxygen. Classification of matter. Matter can either be a pure substance or a mixture. That's it. Every sample of a given pure substance has exactly the same characteristic properties and composition. So it has a uniform composition. It's made up of the same thing every single time. It never changes. Mixtures do not have uniform composition. A mixture might be something like concrete. If you're somewhere near a river, a lot of times they try and use river rocks in the concrete. If you go to the beach, you'll find seashells in the concrete. They're all concrete and mixtures, but they're made different every single time. Well, like a pizza. A pizza would also be a mixture. Differences in physical properties can be used to separate mixtures. Filtration and distillation. If I had sand and water and I needed to separate those two things, I could do it by physical means. I might pour the water and sand mixture through filter paper. The sand would end up on the filter paper and the water would go on through, and I would have separated those two. Distillation involves boiling things, and that's how we will separate petroleum products. It's a difference in their boiling points. Now, a pure substance can be broken down a little bit more into an element or a compound. Those are both pure substances. They have uniform composition. Water is always made of 2 hydrogens and 1 oxygen. You put another oxygen on there, and you have hydrogen peroxide. Not quite as refreshing. Now, mixtures can be broken down a little bit further into homogeneous mixtures or heterogeneous mixtures. Homogeneous mixtures, homo means same, and so it's going to look the same. That would be an example of like sugar water. You would not be able to tell the sugar that it was sugar water until you went to take a sip. It would just look like water, so it's going to look the same. A heterogeneous mixture might be, an example of that would be if you had a mixture of black pebbles and white pebbles, and I ask you to pick out all the white pebbles. You could do that. You could see the different parts. So that's a heterogeneous mixture. Chemical properties and changes. Chemical property is a substance's ability to undergo changes that transform it into different substances. So this is basically how it plays with others. What does it react with? Is it extremely flammable? Does it react with sulfur? Those are chemical properties. A chemical change, and a good rule of thumb, chemical change is a chemical reaction. A change in which one or more substances are converted into different substances. Reactants form products. We have something different. And so the example I have is burning charcoal. Charcoal is carbon, and when we burn stuff, the way we represent that in a chemical equation is O2. That's oxygen gas, because flame needs oxygen in order to proceed. So oxygen gas, that's how we represent fire in a chemical reaction. So when we set carbon on fire, we get carbon dioxide. Carbon dioxide is not like carbon, and it's not like oxygen. It is its own new substance. And that's really one of the best ways to see if you have a chemical reaction happening. Did we form a new substance? The law of conservation of mass. This is a very fundamental law of chemistry, and it's very, very important that you understand what the law of conservation of mass is. I'm going to ask you to repeat it to me. We're going to practice this. Mass cannot be created or destroyed during ordinary chemical or physical reactions. So mass does not magically disappear, and it doesn't magically reappear. It is accounted for. The mass of the reactants in a chemical equation is equal to the mass of the products. So the mass of what you start with is equal to the mass of what you end up with. Energy is involved in almost every chemical or physical change. And that's one of the reasons we study chemistry. We're interested in that energy. Nuclear chemistry, thermochemistry, which has to deal with heat and that type of energy. Electrochemistry, how we can get electricity from chemical reactions. We're very interested in that, and that's one of the reasons why we study chemistry. The elements, their names and symbols are given on the periodic table. And I'll give you a copy of this periodic table. We actually know up to about 118. This is an older periodic table here. Um, it's divided into groups, and these are the vertical columns of the periodic table. They're also called families because they act similar in similar situations. Group 1 is extremely reactive with water, and it gets more so as you go down Group 1. Periods are the horizontal rows of the periodic table. And it is periodic because it is a repeating pattern of those properties. Metals are elements that are good conductors of heat and electricity. They have metallic luster, which means they're shiny. They have high tensile strength. They're malleable, which means that they can be hammered out into thin sheets, and are ductile, which means they can be drawn or extruded into a wire. And they're located on the left side of the periodic table. And we divide the periodic table by the black stair-step line. And so if you are to the left of the black stair-step line, you have your metals. So I'm going to go back over here, and your black stair-step line, it isn't shown right here, but it goes, oops, let's go back. It goes right through here, these green ones, and you'll see why here in just a second. So the left side, and we have copper, we have zinc, we have iron. All of these we associate with metals, silver, gold. Those are things we associate with metals, but it also includes things like that we may associate with minerals or things like that when we eat, like calcium and potassium and magnesium. So the definition of metals is a little bit broader than what you may have remembered. Now you'll notice as we write the symbols for these elements, it's either one single capital letter or it is two letters. First one is capitalized and the second one is a lowercase letter, and that is an important distinction. CO, that O has to be a small one because this is cobalt. But if it's capital C, capital O, that's carbon monoxide, a totally different substance. Some of these don't match the name of what, the English name of what they represent, like potassium is K. And that's because it's given the abbreviation from the Latin name of that particular one. But we're going to use these so much, you'll know them offhand. Sodium here is Na. Hg is mercury. Lead is Pb, from the same Latin root word as plumber, because we just use lead pipes. And tin, as in a tin roof. Nonmetals are poor conductors of heat and electricity. Most are gases at room temperature, and those that are solids do tend to be brittle. They're located on the right of that black stair-step line. They're going to include oxygen, nitrogen. Now, one important distinction there is hydrogen. Hydrogen is very much a nonmetal, even though it's located on the top of group 1. It's there for a reason, which we'll talk about a little bit later. The metalloids, it's an element that has some characteristics of metals and some characteristics of nonmetals. They're located on the stair-step line. They share a border with that stair-step line. Aluminum we generally consider to be a metal, even though it is sharing a border with the stair-step line. All right. I think that's good for today.